So this is a second course in Riemannian geometry, so I will assume knowledge of the basic theory of Riemannian metrics, of calculus on Riemannian manifolds, or covariant derivative, and all the things you can build from that. I will assume like knowledge of curvature and variational theory, a little bit of the theory of geodesic, like completeness, the Hopf-Reno theorem, and stuff like that. And what I will cover, so I give two references. I have some notes which are not exactly on the scope of what I'm doing in this lecture, but I have some older notes that I will share with you at some point. And for references, so yeah, the classics like the book by Peterson is a good second course in Riemannian geometry. And there will be an emphasis on metric Riemannian geometry. And so the book by Burago and Ivanov is a great course on Riemannian, on metric geometry. Okay, so let's go. Maybe a brief outline. So in this first lecture, I will introduce the Gromov Hausdorff distance and give some examples. On like Tuesday and Wednesday, we will talk about comparison geometry for sectional and Ricci curvature and the different approach that you can have. Like we will treat comparison geometry for Ricci curvature using mostly the Bochner formula. And for sectional curvature, we will use like the Riccati equation for the curvature operator, for the second fundamental form of distance hypersurfaces. And the fourth lecture as an intro to the course by Professor Bamler in the second week will be an intro to Ricci flow. Or maybe I should add here another reference for Ricci flow. So yeah, the book by Chow and Knopf is a good intro. An introduction to the Ricci flow. So if you want to take notes, great, but with the marvels of technology, I will be able to share all that I've written on this digital whiteboard with you as a PDF file at the end of each lecture. So don't be too stressed out if you miss something. You will be able to process the information on your own if need be. Okay. So yeah. So let's begin now this first lecture. Let's get to the meat of the subject. So our goal here is to give an introduction to the let me write that in full at least one time. The Gromov Hausdorff distance, which is a basic tool of metric geometry, which will play a role at least in the courses by Philippe and Gilles. I don't remember who's giving those courses, but anyway, so there are courses on Gromov hyperbolic metric spaces and on cat spaces, and they will use at some point Gromov Hausdorff distance. So thought it was a good idea to end the lecture by Mondino. In the second week, we'll also use these tools. So this, if you're as will, I guess the lectures by Sormani and Antoine Song. So this is really a pivotal tool. Okay. So Let's go. But first, so what's the goal? So it has been a trend of Riemannian geometry, let's say starting in the second half of the 20th century, to consider not only its theorem which apply to one specific Riemannian manifold with a Riemannian metric, but to consider the set of all Riemannian metrics or Riemannian manifolds with some geometric condition. And in order to do that, it's convenient to have a topology and a notion, at least a notion of convergence on this set of all Riemannian manifolds of with those conditions. So we need at least a notion of convergence, let's say. And what's so yeah, let's do inspired by what we've learned to do at in school. In analysis, let's do a first attempt, which will not be quite enough, but will have its uses sometimes. And this notion is sometimes called CK convergence. And we will see why it's not enough for our purpose. Okay, so first definition. So let's take a sequence MIGI for I in N of smooth Riemannian manifolds. And we will and let so M infinity, G infinity be another Riemannian manifold. So we say that MI and GI CK converges to M infinity, G infinity if there exists some diffeomorphism phi I from M infinity to Mi. So that's so these are diffeomorphism such that if I take the pullback of GI, so that's a metric on M infinity. So then this is a tensor which lives on a fixed manifold, which is M infinity. And this is going to 0 in CK of M. Okay, so that's a first notion of convergence for Riemannian metrics or Riemannian sequences of Riemannian manifolds. It has some pros and cons. Maybe let's give some examples. So this is a bit limited, but we can already have some interesting phenomenon. So, for instance, if we have C1 convergence, the curvature in the limit can be not well defined. No. So, for instance, you can have, so imagine like a surface of revolution, like a flat cylinder, and you cap off like hemispheres here on each side. And so this can be approximated by smooth surfaces. Like from the inside, you can smooth that. Like there will be like lecture by Felix Schulze about mean curvature flow. And this is a convex set, so this is a really good candidate to be smoothed by the mean curvature flow. And so you can have smooth surfaces which approximate these surfaces which has a C1 but not C2 Riemannian metric. And here, so you see that we can have some non-smooth behavior, but actually this won't be enough. So okay, we also need the non-compact case, which is actually much more useful. And those notions of convergence will be of great use in the Ricci flow setting too. So that's, I think, a good idea to recall them. So for non-compact spaces, this definition is really too restrictive. So we need to get to use like things on compact sets, and so the definition is as follows. So I take a pointed Riemannian manifold, so that's a point in Mi, and I say that it converges to some pointed Riemannian manifold in Ck if okay, so there exists UI open sets in M infinity, which is an exhaustion of M infinity by relatively compact sets, such that I lost my diffeomorphisms. So there exists UI, an exhaustion of M infinity, and there exists phi i's from UI to some open sets, so which is a diffeomorphism on its image, which is in Mi, and such that so phi I star of Gi converges on locally, so on every compact set of M infinity to G infinity. And I forgot the point, so P infinity, which is in UI, should be mapped to Pi. Okay, so maybe now it's time to go inside some examples. So let's consider, for instance, spheres of increasing radius pointed at, let's say, the South Pole. So, okay, that's M1, P1. M2, P2. So, yeah. So imagine this is a very large round sphere, P3, and so on. So the radius of Mn is n. And so this converges as pointed manifolds to flat Rn with the origin, let's say, though it doesn't really matter in that case. Maybe some exercise. So if Mi, Gi, Pi, so this is a very easy one, but quite useful sometimes. So Ck with M infinity compact, then Mi is diffeomorphic to M infinity. Okay, so that's first exercise. Second exercise, which is just a generalization of this. We could, about this example, how do you prove that you could write like the metric in stereographic projection? And for spheres of increasing radius like that, and you will see that actually on compact sets of the chart given by the stereographic projection, the metric really goes to the constant metric. Like you have this conformal factor which goes to 1 more or less if you normalize things well enough. Okay. Now let Mn G be a fixed manifold. Let P be a point in M. So, and the question is, so I take Mn with the same point at each time, and I will just scale the metric like by a big factor. So what does it converge to? And then we can do the opposite. So here there will always be a limit, and we can do the opposite. We can shrink the metric. So here there is always a limit, and it's universal. It's not too complicated. And here the question in assume it converges. Assume C2 convergence, pointed C2 convergence. And find M and G and the limit. Okay. So maybe as an extra example, let me stress that this kind of a pointed convergence really depends on the point, the points you're looking at. So for instance, so imagine like a kind of paraboloid with a cylindrical end like that, which goes up to infinity. And consider a sequence of points going to infinity on this radial geodesic here. Then So yeah, if I don't move my point, so yeah, as I go to infinity, I just go to the same, so nothing's happening. CK or C infinity, whatever you want. But if I move my base point here further and further away, I have CK convergence, and as I go to infinity, to yeah, not M. I will draw a picture. So basically, when you're far away, you don't see what's going on with this compact tip and stuff like that. So what you see in the limit is just a cylinder with a point. Okay. Yeah, we assume it's complete. Thank you for the question, Erwan. And Andre, yeah, P infinity is supposed to be in infinity. You're right. Let me. Yeah, I say it's part in that of that notation. Sorry, I didn't see. I don't have any audio cue when there's something happening in the chat, so I'll try to get to keep an eye on it, but I might lose some stuff. But thank you for the question anyway. Okay, so now maybe let's see what pros and cons we have here. Well, lots of Riemannian invariants are continuous with respect to CK convergence. For instance, if K is greater than 2, curvature passes to the limit. And this is used in at least my solution of the last exercise here. So that's good. We have a lot of continuous functions. So this is a very strong topology. So diameter will be continuous, volume will be continuous without any restriction, and so on. And this is very close to the convergence of functions, the CK convergence of functions which are studied in analysis. And so it's also flexible. We could like replace. So maybe let's go to this definition in the compact case. Sorry, we can replace this by Sobolev norms if it's more convenient to us, or LP if you want very weak stuff, though we will have very few continuous stuff if we just assume LP convergence of the metric. But yeah, but this is flexible. We can change the norm depending on what we want to do. Okay. But yeah, so we have the pros. Now let's go with the cons. So what are the drawbacks here? Well, topology cannot really change, which can be seen as a good thing, but in application, it's so we're very limited. In particular, dimension, for instance, cannot change. So this is one thing, and so things that cannot be addressed with that is the following. So consider a sequence of tori, which are like, so maybe let's keep one radius fixed, and let's consider thinner and thinner tori of this radius. Like a smaller and smaller tubular neighborhood of a circle in space. Boundary of tubular neighborhoods. And so we would like that to converge to a circle. That's what our intuition in space tells us. And this cannot be addressed with that with this framework. Other thing that we cannot address, so this kind of phenomenon is called collapsing. Dimension drops, and so we cannot address that with CK convergence. Another kind of thing that we cannot address is singular limits, for instance. So we could get mild, very mild singularities. That was the example here, like where curvature kind of existed, but wasn't continuous. Actually, this surface would have like some kind of a measure as curvature, and a very well-behaved measure. Like it would be an L1 function, so piecewise continuous. Okay. Let's say no. Let's say that in the Kant we have no singularities. For instance, you can write a formula for that. So consider like smoothing of the cone, for instance. You can view this cone like as the surface of a revolution whose profile is given by the absolute value function, and you can approximate that by like, so that would be y equal absolute value of x, and you can approximate that by stuff like y equal like square root of x squared plus 1 over n squared. And so so this is 1 over n. And you will see that this like smoothing of the cone approach the cone, and you cannot have C2 convergence because the curvature at the tip goes to infinity as n go to infinity. And the limit is not cannot be written as a smooth metric, smooth Riemannian metric. This takes some work because, well, you could write the induced metric in some chart, but the fact that the metric doesn't converge in this chart doesn't tell you that maybe you just picked the wrong coordinates. So you need some things to detect that the limit cannot be smooth Riemannian metric, a smooth Riemannian manifold. And for instance, you can look at the like either the area the area, for instance, of those parts, which should be like metric disks in a Riemannian manifolds, and so they, at a very small scale, they should behave like Euclidean disks, but they don't. Okay, and still in the chords, and this will be related to that, is that compactness for that kind of convergence, compactness like existence of a converging subsequence, is expensive. So let me quote one theorem, especially because it will have a Ricci flow counterpart, which will be of some use, I guess, in the second week. Usually attributed to Jeff Chigger and Mikhail Gromov. So I will do in the non-compact case, because it's maybe the most useful one. So assume like I have a sequence of manifold with the same dimension, such that the sectional curvature of GI is bounded independently of C. And second thing, the injectivity radius of GI at PI is bounded from below. Okay. Then what's going on? Yeah. Yep. So MI, GI, PI has a converging subsequence. So this is a very useful theorem, but like bounding the sectional curvature or bounding the full. So this is equivalent to bounding the full curvature Riemann curvature tensor. This is a pretty expensive assumption, as is having a lower bound on the injectivity radius. So this has a convergent sequence in C1 alpha. And you see we have a two-sided bound on the curvature. And it's not even clear, since we have only C1 alpha convergence, that bound on the curvature will pass to the limit. So this might be, in some case, not satisfying. If we would like more than C1 convergence, we would need not only bounds on the curvature tensor, but also on its covariant derivatives. Okay, so yeah, maybe let's do a quick poll. Sorry. So I will draw a sequence of Riemannian manifolds, surfaces actually. So assume like you have a sphere here, and you attach it to a cylinder. Yeah, let's say, so that's let's say M1, and that would be MK, and you attach it to a cylinder of radius 1/k in some way. So it's, and you keep the sphere of the same size. So in the limit, you expect to have maybe something like that, if you have some kind of limit. So that won't be a Riemannian manifold. So my question is, what's going wrong? So I will put that in the chat in Zoom. Oh no, sorry, I hadn't created the poll yet. So there is no smooth limit here. So what's going wrong in the theorem? Which assumption of the theorem is violated? Is it the bound on the injectivity radius or the bound on the curvature? Okay. Okay, so we have like 18 votes so far. Thank you for your participation. Most of the answers point out that the injectivity radius is going wrong, which is actually true if you're like, yeah, if you're here, yeah, if you're here, the injectivity radius goes to 0. But I was a bit sloppy on purpose, and I didn't tell you what the pointing was. And actually, since I'm not kind of moving my point of view on those manifold, it's more or less, it would be kind of implicit that I'm not moving my pointing. So actually, at the point of interest, the injectivity radius is fine. It's just a piece of the sphere. So yeah, let's assume even that all this part in red is the standard hemisphere of radius 1. So the injectivity radius is at least pi over 2 there. So the injectivity radius is going to 0 at some point, but it's not going to 0 at the pointing. So actually here, this is this. This is going wrong. But the and actually you can see this, because if it wasn't going wrong, there is a theorem that would tell you that the fall off of the injectivity radius when you move away from one point, whoops, is controlled in terms of a bound on the curvature. So yeah, this is a bit subtle, but that's an interesting example. Okay. Okay, now let's go to our second attempt, and which should be enough. So we want, especially given the fact that compact sets are expensive, and that we would like some non-smooth limit, so we are looking for some kind of weak convergence. So we want some kind of weak convergence. So we want a weaker topology. So this will have a big advantage. It will be that it will be much easier to have convergent subsequence. For instance, with this Gromov Hausdorff topology, this will be a converging sequence, as will be this or this. But it will be much, much more difficult to prove continuity of various geometric invariants. So that's that's a trade-off. There's no such thing. Okay, so first, let me give a quick. Okay, let me first do a practical definition, which will be maybe, in my opinion, the most practical in when you're trying to understand stuff and to prove things converge. And then we'll say a few words about more abstract definition, which are easier to prove abstract theorem with, but which are a bit more complicated to work with. Okay, so first definition. Okay. So we take x dx and y dy to be compact metric spaces. We say that f from x to y, epsilon some positive real number. And we say that f from x to y is an epsilon isometry if, so there's a first condition, which is that the distance between point in x and the distance measured in y between their image by f is roughly the same. So this is a very rough measurement. In particular, it doesn't tell anything at a small scale. This is a coarse. They are roughly the same, but at a fine scale, it doesn't tell you anything. And then you need some kind of surjectivity of your map. So, and you ask that up to epsilon, f is going everywhere in y. So for any y in y, there exists some x in x such that the distance between y and f of x is at most epsilon. So one quicker way to write that is to say that y is included in the union for x in x of the balls in y, center that, not x, f of x and of radius epsilon. Or if you want to be even even shorter, you can say that it's you can use this notion of a ball for tubular neighborhoods, more or less, here, of radius epsilon. So this is the definition of an epsilon isometry between metric spaces. Okay, now we can define the Gromov Hausdorff distance. Oops. Didn't want that pen. So the Gromov Hausdorff distance between two compact metric spaces spaces x dx and y dy. When there's no ambiguity, we will tend to just use x and y and assume that it comes with some metric which makes it compact, just to have simpler notations. So the definition is the following. So you want for the distance to be less than epsilon you want epsilon isometries in both directions. Okay, so maybe some example exercise. Okay. Okay, so first is a pretty easy one. So assume d1 and d2 are distances on some set x such that as functions on x times x, so in C0 of x times x, so with the subnorm, yeah, maybe I should. It's not guaranteed that they define the same topology, so this function need not be continuous, so we just tell infinity. It's less than epsilon. Then dgh of x d1 and x d2 will be less or equal than epsilon. Oh, maybe a small another pole. Up. Let's go. Okay, so I've put a poll. So the question is, should there be equality between those? Should the Gromov Hausdorff distance between x d1, or maybe assume, yeah, with this, we change a little bit. Let's assume that the sup is equal to epsilon, and the question is the Gromov Hausdorff distance between x d1 and x d2 equal to epsilon in that case? So this is my question in the chat. You can think a little bit. If you haven't seen that before, it might not be totally clear. Okay, I'll give you a little bit of time to try to answer the question. Okay, so we have 12 answers so far, and we have 10 no's. But we still have 2 yes, so I must explain why this is not enough. Or 3 yes now, okay. I must explain why, even if D1 and D2 could be very different, or at scale epsilon, their Gromov Hausdorff distance might be smaller. And often in those elementary observations about Gromov Hausdorff distance, it's enough to think about finite metric spaces. So assume that xd1 is, let's say, like 3 points like that, with respective distances 1/2, let's say epsilon over 2. That will be better. And epsilon, I think of 2 points at distance epsilon and their midpoint. Okay, and assume that xd2 is the same thing, just assume that we have moved a little bit the points. We have like exchanged, we have put the midpoint on the left. So here we still have epsilon over 2. Yeah. Here we have epsilon. And here we have epsilon over 2. So that would be our distance between our 3 points. The Gromov Hausdorff distance is 0 because these spaces are isometric. Yeah, if you have real isometry, so something which is distance preserving, then you have an epsilon isometry for all epsilon positive, and the Gromov Hausdorff distance is 0. So what that tells us is that the Gromov Hausdorff distance is not a distance on metric spaces, but on metric spaces up to isometry, which is a good thing for the geometers. But here you have an isometry between the two, but the uniform norm between D1 and D2 here is non-zero. Okay. Now, maybe, second exercise. So take xd metric space and gamma inside X finite set. We say gamma is an epsilon net for some epsilon positive. If we're using the notation I introduced in the definition of isometry. That was the second condition, more or less. X is covered by balls centered on gamma, so with respect to the metric D, of radius epsilon. So every point in X is at most a distance of epsilon from some point in gamma. So the exercise would be to compute or estimate from both sides Gromov Hausdorff distance between X and gamma. So basically you have one epsilon isometry, which is the inclusion of gamma in X. would it? Yes, it will be an epsilon isometry by definition, and you can build like some epsilon. So there will be some constants floating around, but maybe that would be a 2 epsilon or 4 epsilon isometry from x to gamma by sending each point in x to some point in gamma, which is at distance at most epsilon. So yeah, maybe let me draw a little picture. So this is gamma, this is x. And so we have epsilon here. And so those balls of radius epsilon cover all of x. And so each point in, to build an epsilon isometry from x to gamma, you just build some kind of projection. You send each point in x to some point in gamma, which is at distance at most epsilon. Okay, so this is a very convenient setting, very convenient tool, because it it moves the study of Gromov Hausdorff convergence to a study of finite sets. Okay, so now okay, and maybe an exercise. No, there is no continuity assumption on epsilon isometries, as you see in this example. And if you look at you cannot prove it from the definition. You could, it's sometimes useful to consider like Lipschitz condition on F rather than this like uniform control. And this would imply that the F is continuous. But this is, like the previous example, this is a bit too strong of a convergence to consider. Okay. I think I forgot something. Okay, so maybe okay. Wasn't too important, I hope. Yeah. Last exercise before we go. So I said that it was complicated to get continuity of geometric invariants using only Gromov Hausdorff convergence. But there is one invariant which is easy to control. It's the following. Yeah. The diameter of a compact metric space is continuous with respect to Gromov Hausdorff convergence. Yeah, maybe and let me add another. Not is DGH continuous, not convergent. Let me add another question. Among finite metric spaces, which we have seen is the cardinality, so the number of points, continuous. Okay, so if you want to get a hand on those things, you could think about that. Okay, so now I promised you a compactness theorem, so I will give it to you. And maybe, yeah, so I guess, what time is it? Okay, let me get it right. Sorry. Okay, I will just copy paste and comment the theorem so that we can think about examples a little more afterwards. So yeah, that's it. So this is due to Gromov, and it is an application of this idea that we were talking about of like trying to get everything through compact sets, through finite sets. Okay, let me. So you have, and we will see that there are natural geometric conditions which give you this kind of hypothesis. So you take a sequence of metric spaces, compact, and you assume that the diameter is bounded from above. So since we have seen that the diameter is continuous, if we want a convergent subsequence, it's a natural hypothesis. And you assume that for every epsilon, there exists some number such that for any I, xi di has an epsilon net with at most n of epsilon point. So basically, you can find in each member of the sequence epsilon nets of a controlled cardinal. Then actually you can, so if you think of these epsilon nets and think about distances between those points, those are like sequences in r to the power n of epsilon times n of epsilon minus 1 over 2. So you can find convergent subsequence of the distances on those guys, and then you use a diagonal argument to build something which is converging on a dense set. That's more or less what's written, which would be like an increasing union of those epsilon nets. And then you need to take a completion, and you will get the limit in the end. Okay. So this is, yeah, maybe let's attribute that important theorem. So yeah, this is due to Gromov, and it's basically using that a countable product of a compact metric space is compact. Or it's the same proof, actually. And this was in the book by Gromov, Lafontaine, and Ponthieu in the 80s, I guess. It was the first appearance that I know of in this form. We will see maybe a little teaser for the next lectures. So corollary. Now if we have a sequence of Riemannian manifolds with a fixed dimension and Ricci bounded from below, diameter bounded from above, then there exists x d and a subsequence ik, let's say, such that L maybe MIL GIL as L goes to infinity converges to XD, a compact metric space. Yeah, that's I think you're right, André. That's all of them converge. Yeah, I guess you need to have like only one point of accumulation in your set. Most often, like when you need to use this compactness theorem, is that you're not. Usually, when you use that, it's that you really need it. When in the end you can prove convergence to some specific stuff, you will prove it directly. You won't need to first extract a subsequence. In the example I know of, usually like or maybe that's not true, but like for like volume rigidity in Ricci curvature bounded from below, you really build the epsilon isometries and stuff like that, and so you don't need that. This compactness theorem like is used in some cases where you cannot tell a priori what the limit is. Okay. Yeah, I will skip that. So there is a notion of pointed convergence that I will skip. But just if you allow pointed convergence, the diameter bound here is not necessary. Just lower bound on Ricci curvature will give you a convergent subsequence in the pointed sense. Okay, maybe now we have 20 minutes. It's time for examples. So yeah, first, like the torus example, maybe I will write it in a more precise way. Not exactly the same, but this is maybe more useful. So consider a sequence of flat 2D tori with one side, so that I will draw as a topologist, and let's say one side of size 1 and another side of size, let's say 1/i. So this is converging to S1, the circle of length 1, let's say R mod Z. So you have this collapsing of in the y direction while the x direction stays the same. You can play a little bit with this idea. Like if you have, for instance, I and one over I, and this will go, so in the pointed sense, so yeah, let's fix some point, to R with an origin. Okay. Also, our like smoothing of the cones. So they converge to the pointy cone in Gromov Hausdorff sense. What other examples did I have? Okay, so one interesting feature here is that here curvature is 0 along the, if you take the flat metric on those tori. And so we have those kind of behaviors. Here, curvature is positive. Those are boundary of convex sets. So this allows for this kind of behavior. And there will be so you can also, so it's harder to describe, but you can like, yeah, how can I describe that? So you can have convergence of a smooth sequence when the curvature is negative to yeah, let me draw it like that. So you have, imagine a piece of paper and you cut it like here, and you add some angular sector here. So here I have 2 pi, and here I add an angle alpha. So that will be a conical singularity of angle 2 pi plus alpha here. And you can have a smooth sequence of metric with negative curvature, which approximate, in the Gromov Hausdorff sense, this kind of singularities. Okay. Okay, maybe let's go to some little more to some richer examples. So let's look at metric on Berger spheres, on the, which are called the Berger metrics on the 3 sphere, I should say. So consider S3 and see it as the set of unit norm quaternions. So this way we see immediately the Lie group structure of S3, and consider, let's say, X, the vector field, which maps Q in S3 to IQ in the tangent space at Q of S3. So, and you can do the same. You have 3 vector fields. They are the left invariant vector fields there are 3 left invariant vector fields on S3, and so G epsilon or GT maybe, yeah, is the metric such that the vector field X, Y, and Z are orthogonal. X, and maybe I should look at my, yeah, X as norm alpha, and Y and Z have norm 1. So these vector fields, you can, using just the the usual computations on quaternions. You can compute their Lie brackets. Once you have their Lie brackets and their norm, you can compute the curvature. So there are several ways to do that. You can compute the Levi-Civita connection from the Lie bracket and those norms. This is not too complicated, maybe a bit messy. Lately, I've been doing that more using orthonormal coframes. I find that I do less error in the computations when I use that. And the Carter formalism, compute the connection form of the coframe and then the curvature form. But anyway, so this is not a computation lecture. So let's write down what we get. So, or maybe let's first think, let's write down what we get. So the sectional curvature is between 1. No. Sorry. Get sidetracked in my notes. Yeah. Is between t squared and 4 minus 3 t squared. If I didn't mess up my computations. And what's going on? So you have, so for t equal 1, it's just the standard round metric of curvature constant alpha. Sorry, I'm changed my notations. So for t equal 1, this is just the standard round spheres. If you look at the integral curves of x, so so we have these 3 vector fields along on S3 here, and the x direction is actually corresponds to multiplication by e to the it. The flow of x is multiplication by e to the it. So let's assume we have p, and we have here would be e to the it times p in the quaternions. And so this is what is called the up fibration on S3. And so we have S1 in red here, fibering we include the fiber in S3, and it projects to S2, and we can actually write the projection using the quaternions, and this is given by Q maps to 1/2 of Q bar IQ. So it goes in a sphere of radius 1/2. Which has curvature form. And what's going on as alpha goes to 0, so you're shrinking these circles, these red circles. So yeah, maybe in a kind of slopey way, but we could say that these circles have a radius alpha, or yeah. Yeah. So when alpha goes to 0, then our S1 shrinks, and all that's remaining is this S2 factor. So we have these circles which shrinks, and the Gromov Hausdorff limit as alpha goes to 0. GT or G alpha? Yeah. Since I will share the notes, let me try to get reasonable notations. So the limit as alpha goes to 0 of S3 with that metric G alpha is equal to S2, but with, say of radius 1/2. Okay? Okay, you can play the same game. I won't write it down, but there is so here we have, it's quite easy to compute the curvature because we have a Lie group, a 3D Lie group. So you can play a similar game with the Heisenberg group, and that will be, I think, an important example. So in the Heisenberg group, you have those vector field x and y, which are inside the plane, and the Lie bracket of x and y is not 0, is vertical, and you can shrink the size of z. So you also need to build a compact manifold. So you can take a quotient by a lattice, and you can shrink the z factor to have collapsing to a torus with fiber S1, which is of something which doesn't carry any metric of 0 curvature, but carry a metric of curvature as small as you want. So if you take a left invariant metric with a z of factor of size about epsilon, the curvature of this metric will be roughly of order epsilon squared, even if x and y stay of length 1. Okay. Where's the Heisenberg group? Okay, maybe last point before we take maybe a small recap. Okay, so I will consider some kind of ellipsoids in R3. And I will assume that this stays of radius 1. So that's, let's say, M0. But that in the vertical direction here, we have something of size epsilon here. So in the section here has still gets size 1. So, and we want the Gromov Hausdorff limit as I go to infinity. Okay, so when epsilon is going to 0, is it going to a sphere or a disk? That's the question. I don't want to be more specific about the setting. Just tell me what you think. What's natural for you? Okay, we have 10 votes so far. Maybe I'll give you a minute before seeing what's going on.
Thomas, do you listen to me?
Yeah, I hear you.
You should stop on time because we have several things to do for the next lecture.
Okay. Okay, so let's take the results. And whatever you answered, you were right, but maybe you were not answering the same question. So we have a majority of disks, and if you consider with the induced distance from R3, you're right. We actually have Hausdorff convergence of this closed set, which implies Gromov Hausdorff convergence to the flat disk inside the XY plane. But here you were right too. But if you consider the induced Riemannian metric on those ellipsoid, and what the limit is in that case is you take two flat disks and you glue them by their boundary. So topologically it's a sphere, and there's a flat Riemannian metric on most of the stuff. Yeah, but with the induced distance from Rn, Christina. Not the induced metric, not the length distance. So you have to be careful with that kind of stuff and that visual intuition. If it goes to the disk, it's when we have when we take just the restriction of the distance as a map from x to x, as a map from R3 times R3 to R. We just take the restriction to our surface. It doesn't come from a Riemannian metric. But if we take the induced Riemannian metric, then the limit is a sphere. But yeah, so we have to be a little bit careful when we think about those stuff. That was an example that I wanted to address. Okay, thanks a lot for your attention and your questions. And see you tomorrow.
Thank you, Thomas. So you can ask questions to Thomas on the chat, and he will probably answer tomorrow.
Yeah, we can do that, exactly.
Okay, I'm sorry, we have to organize the room for the next lecture, and I don't know how to do that. So we need some. Okay, so see you in half an hour.
Okay. Will it be in the same Zoom room, or will it be a different one?
So, no, it's a different one. I mean, there is a room for each lecture.
Okay.
See you then.
See you.